are familiar with Josh. He's an assistant professor at the University of Maryland, and his research interests include soil fertility, nutrient management, and environmental sustainability. He collaborates with Dr. Kleiman, as was mentioned, on the ditch studies here in Maryland, and he's going to present on advanced ditch management to reduce nutrient transport. So I'm going to turn it over to you now, Josh. Thanks.
Thanks, Heather. Thanks, everybody, I guess, for logging in at 3 o'clock on a Friday afternoon to hear about phosphorus. It's pretty unique. There's probably not a lot of people in the world that want to sit around on a Friday afternoon and listen to someone talk about phosphorus. Some of this at the beginning of my talk might be a little redundant with Pete's talk, but he set up the background nicely for me because the foundation of our work is the work that they did down at UMES over the past decade. Really the idea of the ditch filter and some of the other stuff was launched out of that work, and now we're looking at it on the landscape in a few different locations and trying to continue to evolve the technology and hopefully make it better and hopefully make it something applicable that will help us out with our situation there. Pete covered this well. The Delmarva's obviously ditch drained, flat, low-lying area. In Maryland, we've got about 121 miles of publicly managed ditches draining about 183,000 acres, known as the PDAs in Maryland. Over in Delaware, they refer to them as tax ditches. Poultry production, accumulation of phosphorus because we're importing feed for those broilers. It's simple mass balance. There's more pounds of phosphorus coming into the peninsula than there is going out in meat. And so it's accumulated over the past few decades and led to these high soil P levels that we see. And again, Pete showed this figure. This is again just from phosphorus indexes that were run by Maryland planners. And so this isn't all of the soil in the world. This is only high P soil, but it just shows where out of all the high P soils where the highest occurs is down in that lower area of the Delmarva. So I'm going to start out, and again, this covers a few of the things that Pete already talked about, how the project at UMES led us to what we're doing currently. And Pete showed this data, explained it very well, and what we saw were very high. Let me see if I can get my pointer up here. We saw these very high P loads coming from this area here that was a point source. And most of it was dissolved P, although as Pete mentioned, you also have some floating plant matter, algae, some things along those lines that are floating when you have storm flow carrying some P, and that's this portion of that bar, the sediment-bound P, which is not sediment as we would typically think eroded soil necessarily, but probably algae and some things like that that are suspended in these ditches whenever there's storm flow. And all the fields had around the same soil test P concentrations. They're high. They're above the threshold that would prohibit phosphorus application without running the P index. But I've seen a lot higher. But as Pete pointed out, the issue with the really high loads was coming from a point source back there by that manure shed in the poultry houses. Another interesting thing that I think was a real critical piece of information that came out of that study, and this chart I borrowed from Pete, historically we were always concerned when we were talking about managing phosphorus losses, we were concerned with timing of manure application. Indeed, the P index focuses your management on two things, timing and rate of application. Those are included factors in the phosphorus index because we always felt like that timing of applying closest to crop uptake, which certainly helps with nitrogen, but with phosphorus, not sure there's as much benefit, but we said, don't apply right before it rains because you're going to have incidental transfers, and we know that the concentrations coming off of the field, this has been established for some time, concentrations coming off of the field and surface runoff are much higher immediately after application than they are later in the year. So after, a couple of months have passed, that timeline progresses, the concentration drops. But what they found out down at UMES was when they looked at the actual concentrations of the water flowing down the ditch, there was not really a correlation between ditch P concentration and time of application. The concentrations stay pretty consistent throughout the year. And part of this is because, as Pete explained, the source of that water that's in the ditch mainly is coming from underneath the surface. It's subsurface flow. If we look at this chart here, this is flow on the y-axis and 3 years of data on the x-axis, and this is the flow in the ditch, and this is the flow across the surface of the fields. So the majority of the water in the ditch is not coming from the surface. And so when you look at total P in kilograms per hectare, the majority of you've got pretty high P loads in the ditch, pretty low P loads coming across the surface. So the soil is the source of the P, not necessarily the manure that's applied on the surface, and that concentration that's reaching the ditch, most of it's traveling subsurface. So these lessons were very important because when you're talking about managing phosphorus, you've kind of got to know what the pathways are. Where's the phosphorus coming from? How's it being transported? What part of our management strategy can we modify to reduce phosphorus loading? I mean, that's the question we're asking ourselves. And, small areas of the field can be the source. It's not necessarily the whole source, and small ditches can be carrying a big load. But given a high P source, this is the critical part, given a high P source within a field, P loading is then dominated by water export. So you've got to have both the source and then transport. And if the source is there, then the transport kind of is the regulator of the amount of load going downstream. And in these systems, the majority of the P is transported through this shallow subsurface flow. 12 ditches that we've been monitoring now, actually for quite a bit longer, but going back 5 years, the long-term average concentration is 1.67 parts per million phosphorus. We see some pretty high spikes in those ditches, different times. Usually if you get a real high flow rate, as Pete mentioned, as you start up after a storm. But in general, the average concentration going downstream is surprisingly consistent because the source is surprisingly consistent. The source is that soil P that's being kind of leached out and then moving in that shallow pathway. And across the peninsula, this number is proven to be really consistent, and that's pretty surprising. So when we talk about management, we've got these high P soils. What are our options for controlling P loss? Well, historically, efforts have focused on things like riparian zones and buffer strips. There were a lot of questions about the buffer and the grass buffers around the ditches. While Pete was giving his talk, I saw the questions popping up, and I get those questions a lot. And we credit riparian zones and buffer strips with helping with phosphorus transport. No-till, but that addresses particulate P. Band applied P, that reduced application rate, definitely in these really high P soils, we should be cutting out that application to allow drawdown to occur if there's that transport mechanism in place. Timing of application, that addresses incidental transfers, and as we just showed, the incidental transfers aren't playing a large role in what's going down the ditches. We do say no P zones around the ditch, but some of the interesting work that's coming out is that because it's a subsurface pathway, that no P zone isn't going to probably have too much of an influence on what's in the ditch because that water is moving across from the entire field, kind of short-circuiting the near ditch area as far as transporting. And it's still going to take another 50 years to draw down that no P zone along the edge. So there's good science that shows these practices reduce phosphorus and overland flow and losses of sediment-bound P. But our issue isn't sediment-bound P or overland flow in the ditches. It's subsurface flow is the issue. I see a question there from Keith. Has there been any interest in putting in a funnel and gate in the ditch? I guess you're talking about flow control structures to control flow, and actually that's something that I'm going to cover a little bit, Keith. If that's what you're hitting at, I'm going to get to flow control structures. So I guess the way I read it, the strategy that we need to take is stop accumulation and maintenance in critical source area. Critical source area is that field that's contributing P to the ditch. In other words, if there's a field It's got really high source, high phosphorus saturation, and it's connected to surface water. There's a good transport mechanism there. We need to identify the area, and we need to slow down accumulation, maintenance phosphorus applications. Funnel and gate directs water, contaminate water through a treatment zone. Okay. Maybe I'll touch on that in a minute too, Keith. So the P-index does this. Identify the areas where you're at risk with phosphorus connection. Nutrient management planning has done this. Here's some data out of Delaware. Similar situation as the eastern shore of Maryland where these ditches dominate. And what we did is if you look at the green line here, over this 10-year period, we calculate the nutrient balance in pounds per acre per year. Surplus phosphorus, the blue line indicates a management strategy where we took the amount of phosphorus sold in fertilizer and produced in manure in Delaware and subtracted from that what would be recommended application rates per acre in Delaware based on soil test distribution. So we don't have soil samples from every field in Delaware, but the ones that we do have, we extrapolated them out to the entire state. It's a pretty large sample set, so we're pretty confident in this data. The number that we had the biggest question about, one is fertilizer sales. That data is collected, but not great. But the big issue is how much poultry litter is produced, because the numbers we have for poultry litter production are probably on the high side, because these numbers are some old data. And there's some new information coming out, a study being conducted in Delaware now. They just released some data to show it really production numbers that we use in these types of balances are probably overestimating how much manure phosphorus is produced. But even with that overestimation, we get a really good story. As far as the management-based approach, this blue line, it's trending down significantly. We still have a surplus. At the end of this in 2005, what I'm showing here is about 10 to 15 pound per acre surplus phosphorus. We're applying 10 to 15 pounds on average throughout the state of Delaware per acre more than what would be recommended by the university based on strictly a soil test value. And we know this. We know that a lot of soils in Sussex County, Delaware are high in P, and the university recommendation is no P is required for crop production. We allow P application with the P index because that nitrogen and potassium is valuable, but we know that the phosphorus isn't needed for crop growth. Now, the other balance, the green line, this one's really interesting. Phosphorus in and out of the system. So again, we're calculating phosphorus sold as fertilizer and phosphorus produced as manure. And then what's removed through crop harvest is subtracted off. And back here we had a pretty significant surplus. And then we see this big drop. And this is when the nutrient management regulations started to kick in 1999. And also we added phytase to the diet, which reduced the phosphorus concentration in the manure. And we see that it has continued to trend down as we continue to improve poultry diets to reduce phosphorus excretion, because, you know, they're paying to feed that chicken phosphorus to grow meat and bones. The less it's excreted, the better for the poultry industry. And also, as we see, you know, more nutrient management planning, redistribution of that manure. So we see that as far as acres and crop production, we're removing about what we're applying. But we have this surplus in the soil, the savings account, if you will. So cash in and cash out, we're in balance. But we've got a still pretty big soil surplus on some of those fields. The P-index, I think, has had some effect on this, at least as an educational tool. This is for the upper shore and the lower shore, the database from Maryland nutrient management planners. We see that the P-index, if you look here, this is 1% on the upper shore, scored very high over about a 10-year period, 2% high, 8% medium, and 88% low, which means you can apply at an M-base rate. On the lower shore, only about 50% can apply at an M-base rate. 50% had to change their management, apply less than an M-base rate, which historically would have been the normal practice, you can assume. So we see that the P-index has had a big effect in moving some litter around or reducing litter application rates. So the strategy, as I see it again, is once we identify those areas with the P-index, reduce application on those areas or eliminate application, then the treatment options are to reduce water export. You do that through flow control structures to some extent, although there's a lot of mixed data out on the benefit of the flow control structures. But really what you're saying is one of the few things we can do to reduce water export is to increase transpiration, how much the crop takes up and evaporates off. So a high-yielding crop. So people have thought about irrigation. How does this affect phosphorus movement and transport? Because you're definitely relocating water up to the surface. You have higher transpiration under irrigation. The flow control structures are kind of sub-irrigation, where you put boards in there, maintain a higher water level in the ditch over the summer with the growing crop, and hopefully that water is there to feed the crop, and you're transpiring it off and less water is moving downstream. But there's probably only marginal benefit to that, as it's a very flashy system. And then the other option is to address the concentration in the water. So we're really dealing with a concentration issue. If you kind of assume that the flow down the ditch is going to be determined by climate, and we can have very little impact on water export, then we've just got to reduce the concentration in the water as it moves downstream. This is very similar to the gypsum curtain. The gypsum curtain actually kind of evolved out of this concept. Ray started out with the ditch filter, and now he's moved on to kind of pilot the curtains. So I guess that's what I'm going to spend most of the rest of my time talking about is the ditch filters and how they work. And so to get back to Keith's question about having some sort of funnel and gate and direct the contaminated water through a treatment zone, that's basically what we're doing with the ditch filter here. I'm going to show some examples. Overall strategy: the nature of the problem demands an approach that couples targeting, identification, P-index, with solutions to that problem. And in the long term, we need to address the legacy issue, the source issue, stop applying P on high P fields, move it to fields that can utilize it. And we're talking high P from an environmental standpoint, not an agronomic standpoint. A soil can take a lot more phosphorus than the threshold. As Pete mentioned, the threshold for optimum crop production is between, is 50 and 100 parts per million, or FIV in Maryland. But those aren't environmental risk areas. We're not worried about P transport until that saturation gets much higher, and it varies from soil to soil. So you can still be applying manure, poultry litter to fields that are above the agronomic rate. Again, use the P-index to see if you're in a connected area. What's the source situation in that field from an environmental standpoint? Are we above the environmental risk threshold or not? So we're not talking agronomic threshold. We're talking environmental threshold of where we can apply the manures. So, but we need to address that legacy source issue. And then in the near term, if we can control water movement, and we need to reduce the concentration in the water at the source, in this location up in the ditches. So the ditch filter. It's a structure filled with phosphorus-sorbing materials, and we alter the hydraulic head in the ditch with a flow control structure to build a head to push it through that material. So here's a flow control structure in the back of this ditch, one of the sites we've been monitoring for a long time. Put the boards in the flow control structure to build head pressure. You can see it's pretty dry in the summertime, even with the boards in there. We've come up with a couple different designs. We've got we've kind of coined these names: the confined bed filter, stormwater pond filter, cartridge filter, and the tile filter. And I want to talk a little bit about each one, the design, and how they work. Here's an example of what we call a confined bed filter. This is not on the Delaware Peninsula. This is in Stillwater, Oklahoma, on a golf course out there. One of our colleagues, Chad Penn, who used to he did his postdoc at ARS up in Pennsylvania with Ray Bryant and Pete Kleiman before he went out to Oklahoma to be the soil chemist at Oklahoma State University. And so what we've got here is we built a bed on this golf course. Underneath of that slag, that steel slag, quarter-inch steel slag, we just basically, slag's got a lot of fine particles in it, and what we found is it's so reactive with the phosphorus, if you leave the fine particles in there without sieving it first, the fine particles will bind together with the phosphorus mineral that forms and almost form like a concrete, so water will stop flowing through the filter. So first we put the slag through a quarter-inch sieve, so that we only have larger than quarter-inch size slag in this filter, and we're trying out some different sizes to see what the optimum size steel slag is. This filter holds about 3 tons of slag, and we get daily runoff. It's a really nice place to do research. We get a daily runoff events from that golf course because they irrigate every night, which means they're bad irrigation managers, but it's good for us because we get a sample every single day almost from this site. So underneath of that steel slag, there's perforated pipes in the bed of, so running this way, there's a series of perforated pipes underneath of that steel slag, and the water comes into the filter, runs down through the slag, and then it's discharged here by this pipe coming out. So it goes through the steel slag into a perforated pipe and out of the filter. This is a stormwater pond filter, as we call it, or we call it the box filter sometimes. It's a 30-inch by 30-inch wide box by 48 inches tall. That's perforated steel, and that in the middle is a perforated pipe. We surround the perforated pipe with steel slag, same as that other material. We get the steel slag for this. It's a waste product, so it's just the cost of shipping from Claymont, Delaware. We've got this pipe here, and the water, basically the head pressure in the pond drives water through the slag to the pipe in the center and out the discharge. We've got about 2 tons of slag in most of these boxes. We're testing out 1/4-inch slag, and we've tested out 1/8-inch. We tried sieving so that we could get some smaller particles, but not the fines that'll clog up. And this one's actually located on a local poultry farm, poultry production area. So, you know, most of the area is covered by poultry houses or grass or driveways. It's not on a field. Kind of looking at the poultry production area to see how it works. Here's a picture during the summer when it was pretty dry, so you can see we don't have any water running through our filters, but we set 4 of them up. We make them this size. You can make one big one. You can rearrange these any way you want it. We made 4 so that we could get a hold of it with equipment, pick it up, change materials if we want to try some new things. Each one is on its individual discharge. There's a ditch that runs back here in the background. That ditch supplies water to the pond. We've got a flow control structure right here in the ditch, kind of a dam, diverts all the water into the pond. If we have a really big storm, water can go over that flow control structure and go down the ditch without being treated, kind of as a bypass, but we haven't gotten into that situation yet. For the most part, everything comes into the pond, goes through our filters and back out to the ditch. Here's a flow control structure that we can set the elevation in the pond. You can see the boards in there. That's about how high we let the water get, and then it'll flow out, and then if you have a big storm, it can overflow and go out to the ditch untreated. So that's our box filter design. Actually, as it turns out, so far this looks like probably our most successful design. I'll get into that in a little bit. Some of these considerations aren't how much phosphorus a filter removes, but more how practical is it? Does the landowner want to install it? You know, how does it fit into the operation where we're setting it up? This was actually the predecessor, the cartridge filter, before the box filter. These are gravel filters really for an irrigation system. The problem, I'll just cut to the chase, these ended up not working. They work fine. The problem is there's not much of a lifespan. I'm going to talk about lifespan in a little bit, but lifespan is determined by how much material you have out there. I saw some questions earlier with Pete's talk about gypsum, and it's just simply a mass balance. The more material you put in place, the longer it will last. Every material has a different capacity per kilogram of material, but slag's really great, but we just didn't have enough material in these little canisters. But they were nice because they were easy for us to switch in and out and try some different things. So from a research standpoint, they were nice, and they led to the development of the box filter, which holds a ton of material. You know, I could see this being used in a small area, maybe where you have a short-term issue or where you don't mind switching out the material quite frequently. There they are, you know, in place in this ditch with our monitoring equipment set up. We're monitoring all the phosphorus going in and all the phosphorus coming out. That's what the inside of that cartridge looks like. Again, it's a perforated pipe in the center. We filled it with slag around the outside of that perforation. Water goes through the slag and then down out through that center pipe. All of them are toggled together onto one main pipe that goes out past the flow control structure. This is what we're calling the tile drain filter. It's gypsum, so this is just like what Ray Bryant had at UMES. We've got gypsum underneath of perforated pipes. We've got 4 perforated pipes all connected into one. Goes out around our flow control structure. You see our flow control structure in the background. So we put some gypsum down underneath of the pipe, and then we put gypsum over top of the pipe, put our boards in the flow control structure, force the water through the gypsum and out the pipe. Most of our, we've got 3 of these in place, and I think Pete and Ray Bryant have one down at UMES. Ours holds about 50 metric tons of gypsum. You can make them any size you want. That just happened to be the size of our ditch and how much we could get trucked there. We use the same source for our gypsum, and basically it's just the cost of trucking. The PSM, one of the advantages initially that we thought with the gypsum is that there's some utility in land applying gypsum. Some research indicates it increases infiltration in the field, improves soil structure. We're seeing a lot of sulfur deficiency out in the field, and gypsum's a pretty good long-term source of sulfur. It's moderately soluble, so calcium sulfate, it's going to be a good source. And so we were wondering also, after it's been in the ditch for a while, could we clear it out, take it somewhere where they need phosphorus and use it as a phosphorus fertilizer. And one of the things that we found out was that actually it doesn't let its phosphorus go very easily. We did a 1-year incubation study with some of these materials, and they don't let go of the phosphorus they absorb. So it's not really going to be a phosphorus source once we take it out of here, but it does provide sulfur and some other soil structure improvements. So it could be reapplied relatively close to where it came from if it's used in a filter. And some of the stuff about retention time I'm going to get into in a little bit. Retention time is how long water is in contact with the material, and the thing about gypsum is that it prefers a slow retention time. The longer the water is moving through the gypsum, the more phosphorus it can take out. It's ideal for these kind of typical field ditch applications, but you probably want ones where you need a slow flow rate, because that gypsum, it doesn't have a real high flow rate, so a lot of the water overtops it. One of the things that we see here is we've got the flow control structure, and a large percentage of our water doesn't go down through the gypsum into the pipes during a big rain event. A lot of it just goes off down through the flow control structure and never gets treated. So that's one of the disadvantages of gypsum. The gypsum revegetates. This is a couple months after installation, and you can see it's all overgrown just like the rest of the ditch. So it vegetates pretty well out there. So one of our goals was looking at, kind of designing a couple different ways to, different mousetraps. Ray had come up with the ditch filter, and we kind of looked at some different materials and some different physical constructions to get higher flow through. Because that was the big thing in some of the initial work at UMES. We could take 90% of the phosphorus out of the water, but we were only treating 5% of the water. So we wanted to look at some materials and some designs where we could treat 90% of the water. And so we wanted to be able to come up with some guidance that would help with material selection, and that's based on material availability. Again, I'm looking for free kind of waste disposal things. I have a lot of folks, as a matter of fact, I just had someone contact me this week with a material they're interested in us evaluating for the filters. And the question is, if I've got to pay for it, is it really worthwhile when I can get pretty much waste materials to use instead? If it's close by, the cost of transportation is less. That's the main cost in these filters. You have a couple $100 maybe tied up in pipe, but the real cost is the material, the PSM, whether it's slag or gypsum. It's the diesel fuel to get it there. Potential contaminants, there are some issues, and so we test them to see. One of the early concerns with the gypsum was mercury, because they're coming out of a coal-fired power plant and there's some mercury in it, but it's pretty low levels. And then obviously the P sorption characteristics, how well does it remove P, how fast does it work to remove the P, and the physical properties, how fast can the water flow through. And so that's the material selection. And then we've got the structure selection, and that's based on P loads. In other words, how many kilograms per year coming down that ditch. P concentrations is a separate issue, because as you saw with Pete's data, there are situations where you have a ditch maybe with a high concentration, but the load's not as high as a ditch that runs a lot of water. So the material that you pick is very much determined by what your estimated P concentration is as much as your flow rate. Do you want to treat base flow or peak flow? A lot of times you can't get both. And how much slope is out there and available is also a concern. So we're working on design this model. We're hoping to make it a web-based model where you can pop in the measurements for your ditch, maybe estimated P concentrations, and on the website it would generate, how many tons of material do you need, what material would work best, and how long would the filter be good for before you got to change it out. Now it's only a model, so it's a prediction. It's like predicting the weather. It's not 100%, but it's actually the model has turned out to be pretty accurate. We're comparing it to our field data, and it's working pretty well. The way the model was developed was in the lab. They would take small amounts of each material and drip a phosphorus solution on it, and then measure what's coming out the other end. And they'd keep doing it until the material stopped removing phosphorus, because there's a point where that material, just like a glass, fills up with phosphorus and isn't going to hold it anymore, and that's the end of your filter. So we're looking at a model that'll predict that lifespan of the material and lifespan of the structure, and could be used with some simple data on characterization of the different materials, so that if you have a ditch, say you're NRCS, and you're out looking at a site and you're looking at BMPs and you're on the lower eastern shore, and you've got a high P soil, big source, a lot of P going down the ditch. Well, what can you do? I've already been over here. No-till doesn't help. You've already stopped applying phosphorus. Buffer strips along the ditch do you very little good, if any at all. There's just not many options. So, you plug in your data, and it would tell you what size filter you need and what materials and how long it would last. So this is, my slide's a little messed up here. This is an example of what our design curve looks like here. This is electric arc furnace slag, the little triangles, and the squares, the solid ones, and it's different retention times, and this is flue gas desulfurization gypsum. So the FGDG, that's gypsum, slag, and what we did was 1 minute are the triangles and 10 minutes. And the retention time is a liter of water goes into the filter. How long is it in the filter before it gets out the other side of the filter? That's retention time. And you can control this. You can design the filter to change the retention time. We can calculate, if you've got 2 feet of water over your filter, we can put constraints in the pipe to increase or decrease the retention time. And what we see here, it's going to be pretty hard to see, but I've got what I'm looking at is 2 materials, 2 concentrations of ditch water, so to speak. This is lab data, and 2 different retention times. So low concentration, at a low concentration, the 1 minute retention time, electric arc furnace slag does a pretty good job. But if I go to the slag at 10 minutes, it doesn't do a very good job. The slag likes the water to move through it fast. Let's go down here to the 10 part per million. So this is a high P concentration ditch. The slag really prefers high concentrations, and gypsum doesn't. Gypsum does better at low concentrations. The other thing is, look at the triangles are on top here. That's best. This is P added and discrete P removal. So, the first 1,000 milligrams per kilogram, and that's milligrams of P added per kilogram of slag. The first 1,000 or 1 gram of phosphorus added to the 1 kilogram of slag, it removed a pretty high percentage. It moves a real high percentage of that phosphorus, and it just removes less with time. The more P as we saturate that, it flattens out. It's removing less phosphorus with time. But the slag likes a fast retention time. Triangles are the fast retention time. Did better than the squares, which that square 10-minute retention time with the slag, it's going to fail after only 1.5 grams per kilogram. Okay, whereas if I shorten up the retention time to 1 minute, it lasts a lot longer with a fast retention time. So it doesn't last as long. It saturates faster with a slow retention time. So based on the flow-through experiments, they can provide this discrete efficiency of material versus cumulative P added. It's pretty valuable. and they can be used to design the filters based on the chemical characteristics of that PSM. So we're looking at the physical design of the filter based on the chemical characteristics of the PSM of choice. So if you only have gypsum to work with because that's what's close by, then we'd use a curve like this to design the filter so that we'd get the most out of that gypsum for our buck. So faster flow rates, short retention time favors that slag, and a high inflow P concentration favors slag. So if I have a choice of materials, which on the Delaware we typically do, I'd go with slag because I can run it through faster and it'll handle higher P concentrations. Here's a graph that really clearly shows, well, to me it does, maybe it does, tells it to everybody else, the effective retention time. So down here's retention time, 5 minutes, 10 minutes, 15 minutes, 20 minutes. And notice that the solid, again, the solid is slag. The solid triangles or boxes are slag. Down here at less than 1 minute, the slag far outperforms at either concentration, which is 10 parts per million or 1 part per million inflow. This graph shows cumulative P removed in milligrams per kilogram of slag. The slag far, so this cumulative would be at failure. So what I'm measuring here is if I have a filter set up with a 30-second retention time, I've got 1 part per million inflow, it's going to remove about 150 milligrams per kilogram. Whereas if I'm running 10 parts per million, it's going to remove about 600 milligrams per kilogram over its lifespan. So, you know, if I have a 1,000 kilogram filter, I'm going to remove 600,000 milligrams of phosphorus, so on and so forth. And so this is over the lifespan. Each one of these dots would be the lifespan. But what we're seeing is that as we increase retention time, slag becomes less effective. It removes less phosphorus over its lifespan. But as I increase retention time, I can really increase the benefit I get out of gypsum until the gypsum passes the slag up here at a retention time of about 12 to 15 minutes, which is actually really hard to get 12 to 15 minute retention time. And again, this shows the problem we have with our slag filters when we slow them down or gypsum filters, excuse me, when we slow them down that much, you just can't push the water through in a big rainstorm, and so you end up with most of your water going downstream. So I prefer to use slag with like a 30-second retention time, and then I don't have any untreated water going downstream. And one of the things we're interested in is actually mixing materials to try and get benefits of both, and we just haven't had a chance to do that. This shows the effective inflow P concentration. So I've got a ditch with 2 parts per million phosphorus. That's about our norm that we see on the shore. That would be right here. Here's 4 parts per million. 10 parts per million would be really high average. And so these, which are average over the year, and most of them are going to fall right in here. And what we see is I set up this graph to generate 3 different retention times. Half a second for arc slag is pretty normal. Cumulative P removed in milligrams per kilogram. And 20 minutes, 13 minutes, or 15 minutes is the retention time. So down here at these low concentrations, if I could get 20 minutes out of my gypsum, I could have a filter that lasts a pretty long time. But that's unlikely to be able to get a 20-minute retention time. So a 30-second retention time, now that's doable, and the electric arc furnace slag is going to come out by far the best in that situation as far as cumulative P removed. But you can see as the concentration goes up, the slag becomes even more effective. The slope is steeper, which means that higher inflow concentration favors slag. Gypsum starts to perform worse as the concentration goes up, and that's just the chemistry of the system. Basically what's happening with the slag, back up here one with the retention time, the reason why the retention time, if fast-moving water favors slag because of the type of reaction, the slag needs to have the byproducts made from the reaction moved out of the way. Whereas the gypsum wants to have a long contact time because it's less soluble. The material, that calcium sulfate, is less soluble, and you've got to dissolve the calcium sulfate and then precipitate the calcium phosphate. Whereas the slag is a calcium oxide, is what's the main ingredient that's helping you out there, and it's going to dissolve very quickly and precipitate out the calcium phosphates, but it needs that byproduct moved away from it quickly to work best. Filter performance across P concentration. So again, this graph shows a range of P concentrations that we've seen in the ditches from 0 to 10 parts per million. And what I did was I set up, these are actual measurements from our ditch filters. And so our box filters run at about 30-second retention time. It takes 30 seconds for the water from the time it hits the slag until it gets out of the filter. And we got 20 megagrams of slag or 30 megagrams of gypsum. And the gypsum's getting about 12 minutes, 11.5, 11 minutes and 30 seconds of contact time in that gypsum filter. So a much slower gypsum filter, much faster slag. And what we see is that cumulative P removed in grams, that these filters, if I get up to a 10 part per million ditch, the slag over its lifespan would remove about 12 kilograms of phosphorus, and the gypsum would remove, over its lifetime at those high concentrations, only about 6 kilograms, so maybe 7 kilograms. So the slag is almost twice as effective at these high concentrations, but there's not much difference down here at the low concentrations as far as total removal. But remember, I had to slow the retention time down for that real-world filter. Here's cumulative P removal again. So here's cumulative P removed over the lifespan of the filter, and this is P added to the filter. Okay? And so something interesting here is at this point right here, that's your slag, same 20 megagrams of slag, 0.28 minutes. It's actually, I said 30 seconds before, it's actually about 15-second retention time. And after I've added about 10 kilograms of phosphorus, I've removed about 2.5. So as water flows through that, we're removing some of the phosphorus off of the water, but some's going through those. So there's still phosphorus in the water as it comes out, and the same thing with the gypsum. And you reach a point where you're not removing any more phosphorus. And so this has to do with the time when you kill your filter and replace the materials, because as you see, we're doing a pretty good job with a steep slope here early on, and then it flattens out, and at this point you've got a lot more phosphorus bypassing than you did down here. I mean, initially you're removing most of the phosphorus, and then all of a sudden you get up here and most of the phosphorus is passing through the filter. So, you know, you might not want to wait until the filter is saturated. You might want to replace that filter a little bit earlier because the effectiveness has dropped down. So the flow-through experiments show that the slag efficiency improves with the faster flow and a higher P concentration. Slag filters are much smaller than the gypsum tile drain filters in the field. All our slag filters we made are much smaller. And we could make them the same size as the gypsum. It's just that we came up with that box design, and it was easy to do research with. You couldn't do a gypsum in a small filter. It just wouldn't have the lifespan and the flow through that you need. You need a larger surface area to get the flow through you need on a gypsum filter, so you need to fill most of the ditch. And that's why the gypsum works well for the curtains, because you've basically made a giant filter, a lot more surface area that runoff water's hitting. Basically, the slag's going to have less overflow, less flow through of phosphorus. And, you know, we could make a big bed of slag, but one of the things is the farmers I've worked with actually prefer that box filter design, because if they ever get tired of having a filter in the ditch, it's easy enough to go hook it and pull it out. You know, I think it's probably not too hard to go out and dig out the gypsum or dig out the slag if we put a bed filter in with slag, but a lot of times it's just appearances. And the appearance is that box is just easier to manage, so they would actually prefer the box, even though the box is probably going to have to be replaced every year or two, depending on how big it is. I said, you know, I can build you a 20-year filter by making it a bed filter. And they said, I just kind of prefer the box. I can yank it out, dump it, put more stuff in. But our model was really pretty accurate at you can define the lifespan of the filter either by cumulative P added. You know, this filter can take the next 1,000 grams of phosphorus coming downstream, or volume. It can take the next 20 million gallons of flow. And then you just look at average flow or average load from that ditch, and you can come up with how many years it's going to last. So that's basically the story on filter lifetime. Long term, our monitoring the slag confined bed out on that golf course has removed about 50% of the phosphorus going downstream, and that's counting everything. That's counting big storms where stuff went over the top and didn't go through the filter. As the filter got older, maybe it got clogged up with leaves or something. It's about 50% of the phosphorus removed in its lifespan. That's, I think, over 1 year of data. The gypsum tile drain, we've had some problems monitoring the gypsum because of the slow flow through. But actually, I just got some more recent data. This slide's a little bit old. But initial data indicated about 60-67% removal. More recent has brought that back down, but we get a lot of flow over the gypsum past it. So that 60% represents some individual removal rates for some individual storms, but not a lot of data in that because we've had some monitoring issues with the gypsum just from it backing up. The box style filter, we've seen 20% load reduction, but we've got really low loads at that poultry farm. As it turns out, poultry farms are pretty clean. It's not UMES, it's an old poultry farm. It's a modern farm, and we got pretty low loads there. So we took about 20% off long term in the load, and that 20% was when we had some fines in there. And remember how I told you that the filters clog up with the phosphorus minerals that form? That filter was clogged up for 3 months, and all of the phosphorus was going past it. When we take those 3 months out of the equation, we got 50% efficiency. Moved half of the phosphorus. And the way we're doing that is here's flow rate at mean concentration of total P of GRP, and basically 25 to 30% of the concentration is reduced going downstream. To date, the model looks like it's going to predict lifespan pretty accurate, but we need to put some more field data in it. Right now, we got 4 ditches with tile filters, 3 ditches with cartridge filters, and two ditches with the confined bed filter, and 1 retention pond with that box filter out there. We're actually going to get rid of these cartridge filters maybe this summer and put the box filters in there to see how they do in the ditches. And we're working on this website that'll use the model to predict lifespan of the filter. We've got a lot of colleagues that have helped us out or funded this research: Oklahoma State, UMES, USDA-ARS, Chesapeake Bay Trust, DENREC in Delaware, MDA here in Maryland. So I always want to thank them for their help, and I'll put my contact information up there. I think probably most people online know how to get a hold of me.
Does anybody have any questions for Josh?
And I'll open it up for comments if anybody's still awake at 4 o'clock on Friday afternoon. Curtain filter versus the box filter, Craig. It's a good question. I don't know because I haven't worked way too much on the curtain filter. Pete ran off some numbers there per acre. What did he say, about $60 an acre? Is that right? Can anybody confirm that? Haven't done it on a per acre basis. The difference between the filter and the box is fixed costs. So the more acres draining into the ditch, the better. I guess to some extent, same for the curtain. But the box is whatever the price of steel is. I think those boxes cost us a couple $100 to build. We build them ourselves. Craig's volunteering to work on that. Yeah, I actually might have you, if you want to take a look at it. The cost of steel, I think we ended up putting about $300 in our filter. And we're getting the slag for free. I haven't worked out what the cost of the diesel is to bring it down. But probably I'd say you could put in a nice filter for $500 with the box style. But again, a lot of that, it's cost of steel. It's all over the place. There's actually, I should say, there was just a paper that came out on, or it's coming out, I don't know if it's out yet, by Chad Penn, the chemist, put out on dollars per pound of phosphorus removed, and they showed that it was one of the cheapest technologies when they looked at things like buffer strips and no-till, and there's a lot of numbers out there of how much, if you put in no-till, how many pounds of phosphorus do you reduce, and then how many dollars per pound of phosphorus that you reduce, and as they had an economist in Oklahoma do the workup, and they figured out that the filters per pound of phosphorus removed are the cheapest BMP we got. Other questions? Paul, can you put 2 to 3 boxes in line to get higher than 50% removal? So put them in line, yeah. So I guess you guys saw, let me see if I can jump back up here, the stormwater pond filter. There we go. So you saw we put ours in parallel, not in series. So that's, they're all in running into one pipe. And so the question is, can I run phosphorus into this one and then into this one and into this one? That would be the same thing as putting up a big filter. Now in the ditches, we've talked about that. Actually, what we'd like to see done with these filters is put them in the big PDAs, not in the first ditch in the field. And what that would give you is just more acres coming into one filter. The more acres being put into one filter, the better. I mean, we can size these filters any size we want, so we can put these into a giant ditch. The thing is that the Army Corps of Engineers doesn't let you put anything in some of those PDAs because they're considered blue line streams. So if we could get the NRCS to work out something to get us around that, put a big filter in a big ditch, and then have some filters up in the field, so you're cleaning the water coming out of the field, and then that would be a series. So you could have the first order ditch in the field, treat it, and then it's dumping into another ditch with a filter. That would be series, but really to tag them together in line would be kind of just, you could just make a bigger filter to get the same thing, to get greater than 50%. I mean, most of our loss, most of the water that goes through that filter, early on especially, all the phosphorus is removed, especially with the slag. Most of our losses, if we have a really big storm and the water runs out right here, that's the 50% of the phosphorus we're not getting. It's going through here. It's not going through here to some extent, like when these things clogged. And that's when we figured out we had to sieve those to get coarser material in there. So it's really an engineering thing. The chemistry's there. It's engineering. So we're looking at a couple of different designs. One of the things that we talked about is having something to remove nitrogen in there too, in series like you're talking about there, Paul. Question about the whip. I think they have them in there. Saying is, are they in the whip? They're in the preliminary stages, I guess, of being put in the whip. There's a preliminary number in the Bay model, and we're debating what that should be. Right now, it's at 40%, and to some extent, this is a technology I'm promoting, but I'm also pretty cautious because I think we've gotten ourselves in trouble with the Bay model in general, having some efficiencies that are too high. And I'd say 25% is safer because we're still in development. We're still working out the kinks. I mean, someday I hope it would be 90%. But right now I think they've got 40% in as a placeholder, they tell me. I don't know what that means, but it's a placeholder. Is there cost share? I don't believe so, not now. Should be soon. No, we've worked with NRCS on this, the whole project. This was actually initially a conservation innovation grant. So NRCS is on top of this. As a matter of fact, I had the chief of the NRCS out to show him all of our sites here, talked about the technology. My feeling is that at some point it should be. It's just a matter of working out how to do that. I mean, my real indication is this, is, the PDAs spend money on mowing ditch banks and stuff like that. They could just, instead of doing cost share, because that money always bleeds off the more hands it passes through, the easiest thing to do is have the conservation districts go out and put these directly in the PDAs that they control, because they're easy enough to build. Put them right in the PDAs on the big ditches along the road and have the state put them in and maintain them. Because there's no return. It's not like a cover crop. There's no return to the farmer. This is purely an environmental technology to reduce the impact. And if you say, okay, we need to reduce the impact of these high P areas, and as Pete pointed out, 50 to 100 years from now, the soil test P is going to be the same in those fields, pretty much no matter what you do. So we're always going to have 1.67 parts per million phosphorus going downstream. So we got to reduce that concentration. And so if they decide that that's what they want to do, then take your conservation money and just put it into dropping some of these filters at the end of the pipe, treat it like a point source. I can see it. I can see it fall. Yeah. So Craig's saying, you could design a vault and put as many boxes in as possible to get the retention time that you need it. That's something that we've thought about, toggling them together that way. And that's the advantage of why we went to the slag, is because actually we don't need retention time with the gypsum. We do, but with the slag, we can kind of neck it down. But we had talked about that, of kind of putting these together in kind of one unit in a package, and then you could kind of modify some things. So there's a lot of different iterations. It's main thing is getting the money to do the research, because they're cheap to build, they're very expensive to monitor. So whenever we come up with a change, and this summer, other than here at this pond, because it's a pond, in one site in Caroline County, we didn't have any events to measure. It's too dry. There's no water going downstream. And then you miss some events because a piece of equipment breaks or the battery dies, and you really only have a handful of measurable runoff events per year. And a lot of people, I don't think, realize that because we see it raining all the time. We see water going down streams all the time. But measurable runoff events are very few and far between, so you need 5, 10 years of data on one iteration, and you're talking about probably $20,000 in equipment to measure one site, one ditch. And then you're paying for samples at $10 a pop, and we used to sample a lot more, but we're generating 300 to 500 samples a week when we do have water going downstream. So it becomes an expensive proposition to evaluate really thoroughly how well this BMP works. But of course, that's why we guess at most of our BMP efficiencies in the Bay models, because to really evaluate them would cost far too much money. So based on this research, will we eventually see a lower phosphorus site index to eliminate NEP application? I don't think so. I mean, again, it all comes down to transport and soil phosphorus concentration. We're currently getting ready to issue a new P index in Maryland. It's about complete. Pete Kleiman's been very involved in the process, as well as all the phosphorus scientists in the Chesapeake Bay region. And predominantly our P index missed some transport mechanisms. They didn't miss them, it just kind of calculated them incorrectly. And we're adding some new stuff in the phosphorus saturation ratio based on the research from Pete. And so what I would say is this: on the Delmarva Peninsula, my gut feeling is there are enough acres out there that could take all the poultry litter produced on the Delmarva, and a lot of people are surprised to hear that. But when we look at that phosphorus balance, when you get back and you look at that phosphorus balance, it's very clear that we're not producing as much phosphorus in poultry litter as we once thought. When we look at this slide, we see that we got to address this. And if that field is getting 15 pounds extra a year, and it's connected by a ditch, and there's good connectivity, and then we got a problem. But I think there's enough fields with low phosphorus saturation, a little bit further up the shore, that can take the manure. But the new P index is basically the transport, and there's going to probably be more ditch drain fields where we can't apply poultry litter. So I guess the short, I made a short answer wrong. The short answer is that as we look at this, some of those lower eastern shore ditch drain fields are going to have a lot more restrictive with the new P index, because we weren't accounting for all the ditch transport to some extent. I'm looking for my one slide here. I can't remember where I had it. No. Here we go. So, down here, if your P saturation ratio is high, pretty good chance you got ditches and you're connected, so you're probably going to get cut off on manure application, or at least cut down to a P removal rate, so your soil test stops going up. But from here north, there's a lot of places where poultry litter can go, and poultry litter is pretty good price now when you look at the cost of potash and phosphorus. So I think you could easily offset your nitrogen costs if you had poultry litter here, if you dealt it up here, and that's what we'd like to see happen.